I wanted to take a few minutes to talk about plate heat exchangers and fouling factors. Um, we commonly see specs for plate and frame heat exchangers call out a fouling factor or fouling resistance value. While this is appropriate for shell and tube heat exchangers, fouling factors should not be applied to plate and frame heat exchangers. Here's a brief explanation. Heat exchanger capacity can be defined as Q equals U times A times LMTD. A is your surface area, LMTD is your temperature differential, log mean temperature differential, basically your delta T. U is the heat transfer coefficient, and that's the critical piece here. The heat transfer coefficient is a number that defines how effective your heat exchanger is at exchanging heat. The unit of measure is BTUs per hour square foot degrees F. This is just energy per time area delta T. When you apply a fouling factor, it's a D rate of this value. The unit of measure for fouling factor is just the inverse of the heat transfer coefficient. So you have this D rate, and it gets applied like this. Your corrected heat transfer coefficient, U sub F, is equal to your U value inverted, plus your fouling factor. Actually, it's the reciprocal of all that. Let's try out an example for shell and tube first. A reasonable U value for water-to-water shell and tube might be 500. Likewise, a commonly specified fouling factor might be 0.00025, and sometimes it's even higher than that. So if we do the math for heat exchanger where U is equal to 500, you'll get an adjusted heat transfer of 444. Let's say we have a heat load of 1 million BTUs. Going back to our Q equals U times A times LMTD, let's pretend our delta T is 1. Yes, that's silly. It doesn't actually change any of the math here, but your LMTD should be 2 or higher in real life, please. At U equals 500, you would need 2,000 square feet of surface area to meet the load. At U equals 444, you would need 2,252 square feet of surface area. So that's a 13% increase. Now let's look at a plate and frame example. A reasonable U value for a plate and frame heat exchanger might be around 1,500. Yes, that's a lot higher. More on that later. Let's use that same 0.00025 fouling factor and plug it in the same way. Doing the math, our adjusted heat exchange coefficient drops to 1,090. Likewise, plugging that into our 1 million BTU example, your required surface area for that load goes from 667 square feet with the clean U value to 917 square feet with the fouling factor applied. It's a 38% increase. If you enjoy this kind of thing, take your calculator and graph this function, plug in 0.00025 or 0.005 for your fouling factor, and you'll see it's a very non-linear relationship. So using fouling factors on plate heat exchangers will cause these absurd oversizing scenarios, but so what? Well, ironically enough, oversizing heat exchangers will actually increase your rate of fouling and lead to worse outcomes. The physical reason plate heat exchangers don't really need fouling resistance applied is because they have significantly higher turbulence and internal shear stress. This is what gives them their great heat transfer coefficients, and it also means they're naturally self-cleaning. By maintaining a high level of shear stress against the channel plates, particulate deposition is reduced by a magnitude. When you oversize a heat exchanger, this turbulence and shear stress will necessarily be reduced, which will increase the risk of fouling in the first place. And if you're thinking, I bet that's also nonlinear, you'd be absolutely right. So oversizing the heat exchanger will only serve to increase fouling risk and therefore increase maintenance intervals. If you absolutely need to specify a safety factor, the best practice would simply be a flat surface area adder, like 5% or 10%. However, since modern HVAC heat exchangers are AHRI certified, your best bet is to just right-size the heat exchanger and call it a day. Thank you.